Episode 3, C-Check, the Deep Structural and System Review. Of all the systems inspected during a C-Check, few are as mission-critical or as technically nuanced as the aircraft's hydraulic system. It is the muscle of modern aviation, transmitting power where mechanical linkages no longer exist, particularly in fly-by-wire (FBW) aircraft, where the entire flight control logic depends on precise, uninterrupted hydraulic performance. Hydraulics operate the essential control surfaces: rudders, elevators, ailerons, flaps, slats, spoilers, as well as landing gear, nose wheel steering, brakes, thrust reversers, and, in many aircraft, cargo doors and emergency systems. During a C-Check, each of these hydraulic subsystems is inspected, tested, and analyzed not just for function, but for long-term system integrity under pressure. The process begins with full hydraulic pressurization tests, using ground-based hydraulic test stands capable of simulating operational pressure levels, commonly 3,000 psi in FBW airliners like the A320neo, A350, Boeing 777, and 787. These tests are performed in a controlled environment to evaluate leak rates, pressure holding capability, and thermal behavior across the entire hydraulic circuit. In aircraft with multiple hydraulic systems, often labeled green, blue, yellow, etc., each loop is tested independently to verify redundancy and isolation behavior. Faults such as pressure decay, fluid foaming, line vibration, or cavitation noise may indicate deeper issues like internal valve leakage, accumulator failure, or cavitation in power control units, PCUs. Technicians then turn to filter and fluid analysis. Hydraulic filters are removed and opened for microscopic examination of debris. Using magnetic particle analyzers and laser counters, the team assesses the wear profile of the system. Certain debris shapes, like gear tooth fragments or aluminum slivers, can pinpoint which component may be degrading internally, even before performance loss is visible. Fluid samples are also tested for moisture content, acid levels, and phosphate ester breakdown, especially in systems using Skydroll, which is hygroscopic and sensitive to contamination. For fly-by-wire systems, actuator testing is the most critical task. In FBW aircraft, flight control computers issue electrical commands to Electro-Hydraulic Actuators, EHAs, or Electro-Hydrostatic Actuators, EHAs, in newer platforms, which then drive control surface movement. These actuators are typically equipped with LVDTs, linear variable differential transformers, and feedback sensors, and their response time, stroke range, and holding torque are closely monitored. During a C-Check, these actuators are tested both through built-in test equipment, BITE, and manually, using rig pins and control panels. Any deviation from the expected travel profile, signal lag, or unintended movement under pressure, called creep, is grounds for immediate removal and bench testing. Since these components are not field repairable in most cases, prompt detection is critical. Hydraulic accumulators, which store pressurized fluid to assist during pump failure, are tested for pre-charge pressure and diaphragm elasticity. If an accumulator cannot maintain its charge, backup response time may degrade, putting the system out of certification for ETOPS flights or alternate law operation. These are not routine checks. They're critical to demonstrating that the aircraft can maintain control in a triple redundant architecture. Aircraft that have recently undergone major system events, such as overpressure shutdowns, hydraulic fire loop activations, or system overtemp, receive bore scope inspections of long-line runs, particularly in wing-to-body fairings, tail sections, and landing gear wells. These locations are vulnerable to chafing, bracket fatigue, and thermal expansion mismatches. In newer generation aircraft, especially composite-bodied models like the A350 and B787, special attention is paid to hydraulic line interfaces with composite structures. While composites are corrosion-resistant, they are sensitive to hydraulic fluid leaks, especially Skydroll, which can weaken bonding adhesives and stain composite laminates. Maintenance crews are trained to detect early signs of damage, not just mechanically, but chemically and visually. The power control units, PCUs, which house servo valves and hydraulic spools, are another focus area. Their functional response is monitored under both no-load and loaded conditions. Technicians check for thermal drift, overshoot, response lag, and servo lockup, especially in high-cycle components like elevator PCUs, which experience thousands of micro-adjustments per flight. Every step of the hydraulic inspection process during a C-check is accompanied by digital logging and engineering review. If performance degradation is suspected, the component is tagged for teardown inspection or overhaul. If acceptable within tolerance, a maintenance release is signed, accompanied by full traceability and condition reports. In short, the hydraulic system inspection during the C-check is not just a checklist task. It is an engineering-led diagnostic protocol designed to ensure that one of the aircraft's most essential systems is not just functional, but operating within the narrow design tolerances required to support precision flight control. Because in a fly-by-wire aircraft, any weakness in the hydraulic system becomes a weakness in the flight envelope itself. Modern aircraft are as much software platforms as they are flying machines. With the integration of fly-by-wire controls, satellite navigation, autopilot systems, data link communications, and advanced surveillance technology, the avionics and electrical systems on board have evolved into a dense web of critical, interdependent subsystems. During a C-check, these systems undergo a rigorous, structured inspection and testing process, not only to ensure functionality, but also to validate compliance, security, and long-term reliability. Unlike line maintenance checks, where avionics inspections are reactive, triggered by pilot reports or automatic fault logging, the C-check offers a unique opportunity for system-wide diagnostics and lifecycle reviews. The inspection process is comprehensive and often begins with a full digital download of fault histories, performance logs, and BITE data from all major avionics line replaceable units LRUs. Each avionics bay, typically located in the aircraft's nose or avionics compartment, is physically opened and visually inspected. Technicians check for signs of overheating, connector corrosion, chafed wiring, insulation breakdown, or water ingress. Condensation or improper drainage around these components can lead to long-term degradation, especially in composite aircraft where thermal characteristics vary more dramatically. Next, technicians perform functionality testing of flight-critical systems such as Air Data Inertial Reference Units, ADIRS, ensuring that inputs for airspeed, altitude, and attitude remain accurate and stable. Flight Control Computers, FCCs, validating communication between pilot inputs, hydraulic systems, and control surfaces. Navigation systems, including GPS receivers, inertial navigation systems, INS, and backup VOR DME functionality. Autopilot, auto-throttle, and flight director systems, verified using onboard diagnostics and test panels. TCAS and transponders, checked for resolution advisory logic and Mode S interrogation. SATCOM and ACAR systems, validated against connectivity logs and message transmission delays. All tests are executed using a combination of OEM-provided ground support software, aircraft maintenance terminals, and dedicated avionics test equipment. The results are stored and compared against tolerance thresholds defined in the MPD and Aircraft Software Load Configuration (SLC). Equally critical during the C-check is the inspection of electrical power distribution systems. This includes both AC and DC buses, static inverters, transformer rectifier units, relays, and circuit breakers. Technicians verify voltage stability under load, correct switching logic for emergency power sources, bus bar continuity and thermal behavior, battery condition and charge capacity, integrity of bonding and grounding networks. On modern aircraft such as the Boeing 787 and Airbus A350, where electrical power replaces traditional pneumatic or hydraulic sources for many secondary systems, these tests are even more vital. For example, electrically driven environmental systems, brakes and spoilers introduce new modes of failure and require expanded diagnostic routines. In parallel, wiring inspections are carried out using a methodical, zone-based approach. Technicians follow the Standard Wiring Practices Manual, SWPM, to inspect connectors, harness routes, clamp security, and EMI shielding, especially in high interference zones like near radar equipment, or engine pylons. Areas subject to repeated vibration or movement, like the landing gear bay, rudder area, or behind cockpit panels, receive particular attention due to increased fatigue risk. Where discrepancies are found, be it an intermittent signal, degraded insulation, or pin corrosion, troubleshooting teams use time domain reflectometers, TDRs, and cable analyzers to pinpoint fault locations, reducing the need for wide area rework. The C-Check also provides the opportunity for software validation and updates. This includes reloading Flight Management System (FMS) databases, verifying software version integrity against the aircraft's Configuration Deviation List (CDL), and ensuring all avionics are certified against current regulatory and airworthiness bulletins. For aircraft affected by recent service bulletins, NOS SBAs, or airworthiness directives, ADs, related to avionics or electrical issues, such as firmware vulnerabilities, antenna placement, or interference with 5G signals, compliance is often carried out during the C-Check to minimize additional downtime. Finally, avionics maintenance during this phase also looks forward. Airlines increasingly use this window to plan system upgrades, retrofitting ADSB out capability, installing newer SAT-COM modems, or upgrading cockpit displays to comply with FANS-1A or CPDLC mandates for long-haul operations. Every task, every scan, and every diagnostic result during the avionics and electrical phase is logged in the aircraft's Maintenance Information System, MIS. This ensures traceability, regulatory compliance, and the data continuity needed for future predictive maintenance modeling. Because in today's aircraft, avionics aren't just accessories, they are the nervous system of the machine, and the C-Check is where we ensure those neural pathways remain precise, resilient, and compliant.